Hello and welcome to this Revision Monkey video on what's going to be in the Combined Chemistry Paper 2 for 2023. And this video is for those people studying the AQA specification and if you're studying foundation tier. Let's run through what to expect on the Chemistry Paper 2. I'll do a quick recap of evaluate, explain and compare questions. We'll have a look at calculations that you need to know because 20% of the paper will still be calculations. And we'll have a look at required practicals, which are 15% of the exam. And don't forget also lots of skills that we've covered before, things such as surface area to volume ratio, uncertainty, averages, including mean, median, mode, and tables and graphs are likely to come up as well. So have a look through the previous videos in paper 1 for those skills as well. Quick recap of what evaluate questions want you to do. They want you to give advantages, disadvantages, and a justified conclusion to your answer. So these are often between 4 and 6 marks. So they won't tell you that, they just have the word evaluate. So you need to remember to put pros and cons of each thing and give your reason as to which is best and why. For compare, again, it won't tell you, but it expects you to write similarities between two things as well as differences. And also explain questions, they want you to say why, so include as much scientific detail as possible when you're answering explain questions. So 20% of paper 2 is also calculations. So what you may or may not be aware of is that the calculations from paper 1 can also come up in paper 2. So I would again recommend you to brain dump these at the start of the exam. So concentration equals mass divided by volume. That equation could come up again in paper 2. Remembering if your volume is in centimetres cubed, convert it to decimeters cubed first by dividing by 1000 to get that extra mark. And also uncertainty can come up in any paper. So uncertainty is equal to range divided by 2. So brain dump those at the start of the exam and they could come up in paper 2 as well as paper 1. The required practicals that you need to be aware of are rate of reaction, analysis and purification of water, and paper chromatography. Paper chromatography required practical. We use paper chromatography to separate coloured substances. So in this practical, you may be asked a question similar to the one above that says, do food dyes A and B contain chemicals that are in band dye X? So in this practical, we're going to separate 3 dyes, A, B, and another one called X, and we're going to compare the patterns at the end of the practical. In your exam, they might not talk about food dyes, they might be talking about inks or another random coloured substance, but the process is exactly the same. What you need to do to start off with is draw a horizontal pencil line around 2 centimetres from the bottom of a piece of chromatography paper. Do not use pen as this will smudge and spread up the paper. Pencil is insoluble so will not dissolve in the solvent. So this line here that we draw on must be drawn in pencil. On the pencil line, put a small dot of the dyes that you want to separate and label these with pencil underneath. So I've labelled them A, B and X. Place the chromatography paper in a solvent, for example water. The solvent must be below the pencil line. Put it in a beaker with a lid to prevent the solvent from evaporating. Then we leave until the solvent front nearly reaches the top of the paper, then remove the chromatography paper and leave to dry. So the process of separating a substance through chromatography has 2 different stages. The paper itself is called the stationary phase, and when the inks are dissolved in the solvent, that is called the mobile phase. And within the inks that you've put on the paper, you will have different compounds and they will interact differently with the paper and they will have different solubilities. So they will spend different times attached to the paper in the stationary phase and different amounts of times dissolved in the solvent in the mobile phase. So you'll end up separating the substance as it moves up the paper. And to do that, what happens is the solvent moves up the paper, and when it hits the dyes, it dissolves any of the soluble compounds in the dyes. They will then be carried up the paper in the mobile phase, and depending on their solubility, they will stop at different distances up the paper. I mentioned earlier the solvent front. That is where the solvent finishes as it goes up the paper. So if the solvent is moving up and it gets close to the top of the paper, where it reaches here is called the solvent front, and when it gets near to the top, we will then remove the paper and leave it to dry. So the pattern left on the chromatography paper is called a chromatogram. So after we've left it to dry, we will see several dots of different colours on the piece of paper. We would then compare the chromatograms of dyes A and B with the chromatogram of the band dye X. In your exam, you're likely to see a chromatogram in black and white like this, rather than it being printed in colour, and each dot just shows how one of the colours is separated as it's gone up the page. So you can see here dye A has 2 dots and so has dye X, and this top dot here is in exactly the same position as the one on X, suggesting it could be the same compound. Now you'd want to investigate this further to see if dye A does contain one of the chemicals that is in the banned food dye X. Because we've only tested this so far on one solvent, we chose the solvent as water. But to be absolutely sure that our food dye contains a banned chemical, we would need to repeat this in different solvents, for example maybe ethanol. And if this compound in A matched X in different solvents, it's highly likely that it is containing that banned compound. We can't just be sure if we just use one solvent. We must repeat it with different solvents to be absolutely sure. In different solvents, different compounds will spend different amounts of time in the mobile and stationary phases, and what we'll talk about later is the fact that they can have different RF values. The position of this colour on dye A does not match that of dye X, and you can see for dye B it only has one colour here, and it doesn't match at all with dye X. Now because dye B's got one colour and one colour only, this tells us that dye B is a pure substance because it only contains one compound. In the exam you might be asked to calculate an RF value. You do this by calculating the distance travelled by a substance divided by the distance travelled by the solvent. This top line here is representing the solvent front, which is where the solvent got to before we took the paper out of the beaker. And I'm just going to show you an example using one compound here that we found on our chromatogram. Now the important thing is when you're calculating the RF values, you must calculate it from the centre of the dot on your chromatography paper. Not at the top, not at the bottom, but right in the middle of the dot that you're using. And the baseline that we're using is our pencil line where the dye started. So we need to measure the distance travelled by the substance, so this distance here, and then the distance travelled by the solvent. So let's say, for example, the distance travelled by the substance was 400 millimetres and the distance travelled by the solvent was 500 millimetres. Then we do 400 divided by 500 to get us an RF value of 0.8. As I alluded to previously, RF value will be different depending on the solvent used. So this could be, for example, the RF value for water for this particular compound, but if the solvent was ethanol, then this number here would be different. Rates of reaction required practical. When wanting to calculate the rate of a reaction, you might need to use one of these two equations. The first one says the rate of reaction can be calculated by the amount of reactant used up over time, and the second one is the amount of product made over time. So we're going to design some investigations using these two equations. Now, there are several factors that you may be asked about in the exam that affect the rate of reaction. Those include temperature, concentration, and surface area. So you may well be designing an experiment and changing any one of these three things. So that would be your independent variable. And if you change temperature, for example, you need to keep concentration and surface area of your reactants the same. And the same goes if you are selecting a different independent variable. One of them you change and the other two you have to keep the same. There are several different practicals that you can do to calculate rate of reaction, and any one of these may come up in the exam. So this first one focuses on the amount of product made over time, and the independent variable that we're going to change is concentration. So we'd measure 50 ml of 0.1 molar hydrochloric acid using a measuring cylinder and pour it into a conical flask. We'd place, for example, 1 centimetre of magnesium into the conical flask, attach a gas syringe and start a timer. So in here we'd have our acid and our piece of magnesium, which you should know is going to create hydrogen gas. To calculate the rate of reaction in this experiment, we could record the volume of gas produced at regular intervals, for example, every 30 seconds for 5 minutes. And as gas is produced by the reaction, the gas syringe will move outwards and you can measure the volume of gas produced. Do not write amount, you must use the word volume. Then we would plot the volume of gas produced against time on a graph, and we can use this to calculate the mean rate of reaction, and I'll go through how we do this later on. We then repeat the experiment for the following concentrations of acid. So this will be our independent variable, the concentrations of acid. The dependent variable would be our volume of gas, which we then turn into our rate of reaction down here. And important control variables are things such as the volume of acid that we are using, the length of magnesium that we're using, and things such as temperature as well. As in all experiments, it's also really important to talk about the fact that you're going to repeat the experiment 3 times and calculate a mean for each concentration of acid that you're using. So a different practical setup now, but still looking at how concentration affects the rate of reaction. This time, this focuses on the equation the amount of reactant used over time. So we start off by placing a conical flask on a balance and zeroing the balance. We would then measure 50 ml of 0.1 molar hydrochloric acid and pour this into the conical flask. And we then place 1 centimetre of magnesium into the conical flask and start a timer. We take the initial reading on the balance as well, so we're starting off with a mass of 25 grams. Now again we're using magnesium and acid, so we're producing a gas, and because we have no bung on the conical flask, that gas is going to be allowed to escape out of the conical flask. And in doing so, because mass is escaping from the system, the reading on the balance is going to go down. So to calculate the rate of reaction, we can record the mass on the balance every 30 seconds. So we'd wait 30 seconds, write down the new mass, another 30 seconds, again writing down the mass, and so on, and so on. And then we plot the mass against time on a graph, and we can calculate the mean rate of reaction. We'd repeat this experiment for the following concentrations of acid: 0.5 molar, 0.7 molar, and 1 molar, and as always is good practice, right at the end that you're going to repeat it 3 times for each concentration and calculate a mean. A third practical that you might see in your exam, again answering the same question, we're changing concentration and measuring the rate of reaction, is when you draw a black cross on a white tile or piece of paper and place a conical flask on top. We'd measure 50 ml of 0.1 molar hydrochloric acid using a measuring cylinder and pour that into the flask. And we'd also measure 50 ml of sodium thiosulfate using a measuring cylinder and pour that in the flask as well. So you can see at the moment when we've put the acid and sodium thiosulfate in, we can still see the cross because the solution is colourless. However, gradually over time, a precipitate will form to make the solution go cloudy, and at that point we will no longer be able to see the cross. So you can see now, when the solution has gone cloudy, we can no longer see the cross, and we then record the time it takes for the cross to completely disappear. Obviously this is subject to error because different humans will have a different opinion on the exact time that the cross has disappeared. We'd repeat the experiment for the following concentrations of acid: 0.5, 0.75 and 1 molar. And for this one, because we're not measuring the amount of reactant used or the amount of product made over time, we're simply looking for the time it takes for a colour change, we could use the equation rate equals 1000 divided by time to calculate a rate of reaction for each concentration that we're using. So with the results of a rate of reaction experiment, you may well be asked to draw a graph or do some calculations using a graph that's provided to you. So let's look at this graph here first of all. This might be a graph that we might have drawn from the first experiment, whereby we were measuring the volume of gas produced over time. A few things about rate of reaction graphs to start off with then. The steeper the gradient, the faster the rate of reaction. So you can see this first section here is really steep. Then a shallower gradient here, so the rate of reaction is slowing down. And at this point here, where the graph starts to level out, the reaction has actually stopped. And we know that because if you read off the graph here, no more gas is being produced. So here are some common questions that you're asked. One here says, what is the mean rate of reaction? So to calculate this from the graph, you would find out the point where the reaction stopped, draw a line from the x-axis up to that point, and then a line across to the y-axis. And you would read off from the bottom the time that it took, so 15 seconds, because from 0 to here is 15 seconds, and the volume of gas produced in that time, from the 0 up to here, so 34 approximately. And then we would calculate that by doing 34 divided by 15, giving us an answer of 2.3 centimetres cubed per second. We always do the y divided by the x in our calculations, and we get the units for rate by reading them off the graph. Centimetres cubed divided by seconds is what we've done, so those are our units. They could also ask for a mean rate of reaction for a particular time point. For example, what is the mean rate of reaction between 4 and 12 seconds? And in that case, at time point 4, you draw a dotted line up and across to the y-axis. You do the same for 12, and then you would read off between those two sections. So between 4 and 12, we've got a time of 8 seconds, and between our two markers on the y-axis here, we have a volume of gas produced of 12.5 centimetres cubed. So to calculate the rate of reaction, again we do the y divided by the x, so our y value is our 12.5 divided by our x value of 8 seconds. 12.5 divided by 8 gives us, for that section of the graph, a mean rate of reaction of 1.6 centimetres cubed per second. Analysing and purifying water required practical. For this practical, there are 3 different things that you might be asked to write about. The first one is testing the pH of water samples to see if they are in the potable range. The second one is to test the water samples for dissolved solids. Do they have a low enough amount of dissolved salt to make them potable? And finally, if they are not potable, how can we use distillation to purify the water sample? So the first 2 relate to analysing the water, and then the distillation refers to purifying the water. So looking at the first step then, testing the pH of water samples, we would use a device called a pH meter, or sometimes you may see it called a pH probe, but pH meter is best. All you do with the pH meter is put it in your sample, and then it will give you a reading of the pH digitally. So I've got 3 different samples here. I've got some rainwater, some spring water and some seawater. And I put my pH probe in the rainwater, and I would then record the pH in the table. Repeat that with spring water and record the pH, and finally with seawater and record the pH. Now, are they in the potable range is the question that we're looking at. Are these safe to drink? Well, the potable range is between pH 6.5 and 8.5. So you can see here that the spring water and the seawater in these examples are within that pH range, so they could be potable, but the rainwater is too acidic. Okay, it falls below that pH range, so it is not considered to be safe to drink. But we don't yet know if it's potable or not, because it also has to have a low enough amount of dissolved salts and, of course, a low enough amount of microbes. The second part is then testing the water samples for dissolved solids. So we're going to look if they have a low enough amount of dissolved salt to make them potable. This is the equipment that we are going to use. We have a balance here. We've got our Bunsen burner on a heatproof mat with a tripod and gauze. And then we have a beaker, and this beaker is just acting as a water bath. It's just full up with tap water, and on top of that you've got an evaporating dish, and that is where you are going to put your water sample in your evaporating dish. All this water is doing is just acting as a water bath that will gently heat the evaporating dish. It's much better and much safer to do it this way rather than putting the evaporating dish straight upon the gauze. You can also get electronic water baths that will do this as well, which you may see in an exam. So the method for this, we are testing to see if this water sample has dissolved solids in it. So we're going to record the mass, hence the balance, of an empty evaporating dish. We are then going to measure 5 millilitres of one of the water samples, for example rainwater, using a measuring cylinder and add this to the evaporating dish. So we pop our small amount of water in our evaporating dish like so. We then heat gently over a water bath until all the water evaporates from the evaporating dish. Now, to do it safely in the lab, what you might do is allow most of the water to evaporate and then leave the rest to evaporate slowly. But once the water evaporates, you'll be left with none in your evaporating dish. And you will allow that to cool and then re-weigh the evaporating dish. You would then record any mass change of the evaporating dish, if there is any, and observe any salts left on the evaporating dish. So once the water had evaporated, if your sample contains salts, it would likely that you would see salt deposits building up on the sides of the evaporating dish. So when you were to put that dish back on the balance and reweigh it, you'd expect it to be heavier because it now has salt on it. You would then repeat steps 1 to 6 with the other water samples, for example if we used salt water and spring water. So when you look at your results, just because one of the samples may have a low amount of dissolved solids, a low amount of dissolved salt in this case that we're looking at, it might not mean that it is still potable, even if it passes the pH test and the low amount of solids. You would have to make sure that it has a low enough amount of dissolved microbes. So if your water samples are not potable, you can use a process called distillation to purify the water sample. I've just used a different colour here just so we can make it obvious, but let's suggest that in here we put our salt water, because this is what many countries such as Saudi Arabia would do because they don't have much rainwater. And this will allow them to access drinking water from their normally non-potable salt water. So the flask that we put this in is called a round bottom flask, and you would heat that flask normally using a water bath or perhaps using a Bunsen burner if you're doing it in the lab. You have a thermometer at the top here, which you'd want to make sure for pure water was reading 100 degrees C, so that you know that in your beaker over here you are getting pure water. So as you heat the salt water, the water will evaporate and it should leave any salts behind in the round bottom flask. The water will evaporate and it will turn into water vapour and it will go up the tube here. This piece of equipment here is called the condenser, or you might see it written as the condensing tube. So the condenser is kept cold by this cold water going in and around the glassware. It doesn't mix with what's in the middle, it just goes around the glassware to keep it cool. And as the water vapour comes in here, it is then condensed into a liquid, and then it will collect as pure water in the beaker. So in this purification process, we would test the pH of the water using a pH meter. We would neutralise it if we needed to by adding alkali if it's acidic, or adding acid if it's an alkali. And we use a pH meter, not an indicator, to determine when it's neutral. Because if you're trying to purify a sample, there's no point adding an indicator like universal indicator in there, because you're just contaminating it. And a pH meter is going to give you a much more accurate result. So then we pour the salty water into the distillation apparatus, and we said specifically it's the round bottom flask it goes in, and we heat it. And the distillation process, as discussed, will leave us with pure water in our beaker, and we would then just retest the pH at the end to check that it is neutral. Okay, moving on to some content then for chemistry paper 2, topics 6 to 10. A little bit more on rate of reactions first. Just looking at these graphs like we did before, you might have massive product over time. The time might not be in seconds, you might have it in minutes or hours, depending on how quickly the reaction takes. And you might need to identify which is the fastest rate. So we said before, the area on the graph with the steepest gradient is the fastest rate of reaction. So if you're describing it, let's look at line A here. This is the fastest rate of reaction at section 1. Then the rate of reaction slows down as the gradient gets shallower, and then it's a much slower rate of reaction, and then it stops again. So you could describe how the rate of reaction changes, or you might be asked to select the fastest rate of reaction out of 3 lines. In this case, that would be A. We said we come back to the catalyst. We said before that it provides an alternative pathway with a lower activation energy. That's the GCSE bit. You won't get all the marks if you just say that it speeds up a reaction. Remembering reaction profiles from paper 1, they may well creep into paper 2 as well, because you might need to show on there how a catalyst is providing an alternative pathway. If you remember before, the activation energy is this line here from the bottom of the reactants to the peak. So if we're drawing a line with a lower activation energy, you would draw a line on like so, lower than the previous line. So whether it's endo or exo, you do exactly the same thing. Reversible reactions are reactions whereby the reactants make products, and then the products can react again to make the reactants. The symbol for reversible reaction is here, and you will have to be able to draw that in the exam. And one example that they talk about is in the specification is hydrated copper sulfate. That's got water in it. So think to yourself, the one that's hydrated with water is blue. And then that will break down into anhydrous copper sulfate. That's a posh word of just saying the water's gone. Okay, anhydrous copper sulfate, which is white, and water is released. So this reaction here, if you've just got one substance which you heat up and break down to form 2, the forward reaction here is called a thermal decomposition reaction. And if you ever see this kind of reaction, it means it's not reacting anything. It means you need to take in heat to break it down. So this one is endothermic, going in this direction, because it's taking in heat in a thermal decomposition reaction. And in a reversible reaction, if one direction is endothermic, the reverse has to be exothermic. Looking at organic chemistry then, let's start off with this general formula. This says CnH2n plus 2. This is the general formula for an alkane. What the N means, you probably use this in maths, it just means for any number of carbons, you will have double that plus 2 hydrogens. So for example, if we had 2 carbons, C2, we would have 2 times 2 plus 2, which would be 6 hydrogens, and that would be one formula of an alkane. Let's look at the ones you need to know then. You need to know methane, that's CH4, ethane, propane, and butane. So monkeys eat peanut butter is one way to remember the order. Methane has 1 carbon, ethane is C2H6, and that has 2 carbons. Propane has 3 carbons, so that's C3H8. And butane, if you were asked to draw one, think to yourself, monkeys eat peanut butter, so that has 4 carbons. Start in the middle there. And every single bond is a single covalent bond in these molecules. And they are full up of hydrogen ions. And this has got hydrogen atoms, hydrogen atoms. And this has a special word. If it all has single bonds and is full up of hydrogen, this means these are saturated molecules. Think to yourself, S saturated, S all single bonds. Let's finish this one off then. Butane, if you're asked to write the formula for it, C4H10. Now these formulas here are called the displayed formula. So if they start talking about displayed formula in the exam, that's just the one that shows all the bonds in between them. So these are called hydrocarbons because they are just made up of carbon and hydrogen and nothing else. And we can burn these in a combustion reaction. Let's take methane, for example. When we burn methane, we're reacting it with oxygen in the air, and the products are always carbon dioxide and water. And obviously this can link to global warming. So ethane and oxygen would still make carbon dioxide and water, and propane and oxygen would still make carbon dioxide and water. If there wasn't enough oxygen in our reaction, we would do something called incomplete combustion, which is not very good. It produces a really smoky flame. And let's say methane and oxygen, we'd still produce carbon dioxide and water as before, but with incomplete combustion, we'd also produce carbon, which is soot, so solid black carbon, and carbon monoxide, CO, carbon monoxide, and that's bad as well. So the soot we'll talk about later causes global dimming, and the carbon monoxide is toxic and can kill you. Okay, so that's the alkanes. Fractional distillation then, this is where we are separating different substances by their boiling point. So when we dig down for crude oil, that has taken millions of years to make, it will be a mixture of hydrocarbons. You'll have some short ones, some very long hydrocarbons, and it will be a complete mixture, and it's not useful whilst it's a mixture. So the point of fractional distillation is to separate these. You heat the crude oil with a fossil fuel probably, so coal or something used to heat the fossil fuels. And then you are going to separate them by their boiling points. So the shortest ones have the lowest boiling points and they go to the top. Then you get your longer ones until you get right to the bottom where you've got very long chains. The ones at the bottom have a really high boiling point. So they come out of the bottom of the chamber because they're still next to the heat. They're still heating up, but they're not quite at that stage where they've boiled and risen up the tank. So you don't need to know the names of the products that come out of here or the order, but they're things such as petrol and diesel and gases. So gases come out the top, then you've got things like petrol and diesel. Petrol is slightly higher than diesel, and we'll talk about this in a minute, because if you needed petrol but only had lots of diesel available, you could crack that diesel because it's a longer chain and produce petrol to meet the demand of the population wanting petrol. So what can these be used as? Well, they're really useful fuels. The ones at the top that come out are really flammable, so they catch fire easily. They're very volatile, trying to say both things at the same time, which means they easily turn into a gas. So those are the ones at the top, low boiling points, flammable and volatile. The ones at the bottom have high boiling points, they're the long chains, and they are described as being very viscous. That means they are thick and gloopy and don't flow easily, whereas the ones at the top flow easily. They can be further processed to produce things such as solvents, lubricants, and polymers, which we'll come on to later. But in their raw source, they're best used as fuels. So we said before, if you wanted to produce a shorter chain like petrol from a longer chain like diesel, you could go through the process of cracking. Cracking takes place using a heat, I'll just get rid of that writing, using heat and a catalyst to break up a larger molecule. Now, it could break absolutely anywhere. It could break here and make two molecules, or it could break here and make two molecules. It doesn't matter where on the chain it actually breaks. So let's say we started with a long molecule like C8H18. When you crack it, you produce another alkane with single bonds and something called an alkene that has a double carbon-carbon bond. So the alkane, let's say for instance, you could put any products here in the exam. Let's say the alkane that we produced had 5 hydrocarbons, so it would be C5H. We need to double that up and add 2, so 12. So we use 5 of these, leaving 3, and we've used 12 of these, leaving 6. The product that you make will be an alkene. So that would be C3, because we've got 3 left, H6. And this time you can see that it's just double the number of carbon, not double plus 2. So this is what cracking makes, alkanes and alkenes. And alkenes have a double bond. So this one would have 1 double bond between 2 of the carbons, and then the rest of them are single bonds. Like so. For foundation, you won't be asked to draw these alkenes. You'll just need to know that cracking produces an alkane and an alkene. So C3H6. So you could have cracked that another way. Okay, you could have 3 carbons here and 5 over here. It doesn't matter what the products are, as long as they all add up to C8H18. The test for alkenes we need to know about is bromine water, and that goes from orange to colourless in the presence of alkenes. In alkanes, it will just stay orange, so you'll know where your alkene is because it will go colourless. So there's 2 types of cracking. One of those is steam cracking. So for this process, you would vaporize your hydrocarbons, so turning them into a gaseous vapor, and mix them with steam and heat them up, and that will then crack your hydrocarbon. Or you may well see something called catalytic cracking. It's got the word nearly catalyst in here, and this is where you vaporize the hydrocarbons again, but this time pass them over an aluminium oxide catalyst, and it will do the same process of cracking the molecule. So, chemical analysis. You need to know the test for some different gases. Hydrogen is one. If you put a lit splint in the sample and hear a squeaky pop, that means you've got hydrogen present. For oxygen, if you place a glowing splint in a sample, so you've lit it up and then blown it out so it's glowing slightly, it will relight if oxygen is present. Carbon dioxide, we should hopefully know this one. You bubble it through lime water, and if carbon dioxide is present, the lime water will turn cloudy. And again, like previously, because a precipitate has formed, a solid precipitate has made it go cloudy. The final one, chlorine, got to get this correct, bleaches damp litmus paper. Okay, so that's the test for chlorine. You might have touched upon that when you did electrolysis in paper 1. Let's talk about different compounds then. Some compounds are pure. Okay, so some materials are pure. They only contain either one element or one compound, nothing else. Others are specific formulations. Now, this is the definition you'll need to know. It's a useful mixture made from a recipe or a formula, you could write, for a specific purpose. So, for example, paint is an example of a formulation. In paint, you've got the pigment in there, you've got the resin in there, the binder in there, and they are all in specific amounts to make that particular useful purpose. Pure substances you will recognise because they have very specific melting points and boiling points. For example, you'll know if a substance is pure copper because it will have an exact melting point of 1083 degrees. It will have an exact boiling point of 2567 degrees. You find these data tables online, and they tell you the exact melting and boiling point of a pure substance. If you had a mixture or something that was impure, or a formulation, for example, you would not have an exact melting point for copper. So let's say you had a particular sample and the exam tells you that the melting point for copper was 1080 degrees. Even though that looks very close, that is not accurate, is not close to the true value. So this would be an impure sample of copper. It would contain some impurities, perhaps a little bit of sulfur or something like that. So only if they are exactly what the table matches can we class them as pure. Accuracy, if that comes up, in terms of these constant values here, they are accurate if your value is exactly the true value. So, chemistry of the atmosphere then. Scientists believe that the Earth began around 4.6 billion years ago. At that time, there was lots of volcanic activity, releasing gases such as nitrogen, carbon dioxide, ammonia, which is NH3, carbon dioxide, methane into the atmosphere. And the early atmosphere was very much like that of Mars and Venus today. So we went from an atmosphere that had lots of carbon dioxide in it to an atmosphere that now contains, comparably to everything else, very little carbon dioxide, loads of nitrogen and some oxygen as well. So how did it do that? Well, some water vapor was released from the volcanoes as well. That water vapor condensed to form the oceans. As the Earth started to cool down, the water vapor that was in the air condensed to form the oceans. And when that happened, a lot of the carbon dioxide from the early atmosphere dissolved into the oceans. And there it made the shells of early marine organisms. So it made the shells of, we call them calcium carbonate shells, of lots of different marine organisms. It also, whilst it was being dissolved in the ocean, over millions of years, it would have also been crushed down into fossil fuels. So these calcium carbonate animals that died would have been crushed down and locked up in fossil fuels. As well as that, because this rock type occurs at the bottom of the seabed, they would have also been locked up in sedimentary rocks. So you had a situation where you've got lots of carbon dioxide in the early atmosphere, but as it's getting dissolved in the oceans, it is getting locked up in fossil fuels, sedimentary rocks, and in the production of calcium carbonate shells. As well as that, before the animals came along really, we had algae around 2.7 billion years ago. 2.7, sorry, my writing, billion years ago. We had algae forming and plants a little bit later on, and they took in the carbon dioxide in a process called photosynthesis, which you should be aware of. And in the process of photosynthesis, they took in the carbon dioxide and they released oxygen. So the levels of oxygen in the atmosphere started to rise, which sustained other life. Until we got the composition of the atmosphere as it is today, okay, which is 80% nitrogen, approximately, that's rounded up. 20% oxygen, again, that's rounded because together they make 100%, but obviously we've got a few other gases. We've got carbon dioxide, 0.04%, and other gases like argon, water vapor, and things at less than 1%. So it's weird, but in the exam they will round these figures up and down normally, so it might not add up to 100% altogether. So an atmosphere of mostly carbon dioxide, dissolved in the oceans, made sedimentary rocks, fossil fuels, dissolved, made the carbonate shells of animals, and then taken in by photosynthesis, oxygen released, and we end up with the atmosphere like it is today. So chemistry of the atmosphere continued then. We're going to look at global warming. We touched on this in biology, so hopefully you'll remember my way to remember it, which is the soot sun produces the soot shortwave radiation, and that can go through the greenhouse gases, which provide a blanket around the Earth. So these are things like carbon dioxide, the first one, methane, and the lesser known one is water vapor. So always write carbon dioxide first and then methane and water vapor. So the shortwave radiation goes in, but all of the objects on the Earth absorb that radiation and reflect it back into the atmosphere. But this time, as it goes out, it is now long wave radiation. And that doesn't just go straight through the greenhouse gases. Some of it does, but some of it is absorbed and re-radiated back to Earth. So that is what is causing the global warming. The shortwave radiation goes in, it's reflected off of the Earth as long wave radiation, and the greenhouse gases absorb and re-radiate that back to Earth, causing a warming effect. Now we need that to some effect to sustain appropriate temperatures for life on Earth. But however, carbon dioxide levels are going up as well as other greenhouse gases, and that means more long wave radiation is being re-radiated, causing a warming effect. This is causing many consequences, including increased flooding, sea levels rising, changes in species distribution. So some animals are becoming extinct in different areas of the world because they can't adapt to the changing conditions, or they might move places. Okay, so this is meaning they're perhaps migrating away and moving to different areas. Increased frequency of extreme weather, so hurricanes and tornadoes and things like that. So there's a few of the consequences. And it's important that we all consider our carbon footprint, because it's the carbon dioxide levels that are going up. Our carbon footprint is the amount of carbon dioxide and other greenhouse gases released over the full life cycle of a product. So this could be anything from a company making a mobile phone. You could be talking about your own carbon footprint in your day-to-day life. You could be talking about the carbon footprint of a festival, a music festival, for example, and it's the total CO2 that's released. So it's in things such as transport to and from a place. It's in things such as fossil fuels and burning fossil fuels to generate electricity for certain things, etc., etc., and how those can be cancelled down. For example, many people are reducing eating meat, okay? And at the same time, they might be eating perhaps vegetables or fruits that come from far away in the world. So if you're eating perhaps avocados from somewhere exotic, they might be traveling on a plane and releasing lots of fossil fuels. So food itself will have its own carbon footprint. So that's something important to consider as well. Let's look at the main pollutants then. These are the links, and you'll see tables like this in the exam. Carbon dioxide, I want you to always link to global warming, as well as the other greenhouse gases. Solid particulates, for example, we talked about soot or carbon being produced in incomplete combustion, cause global dimming. They sit as a layer in the atmosphere and reduce the amount of sunlight going through. Sulfur dioxide. Now, this is such a common thing in paper 2 to talk about sulfur. Might link into the purity of fuels. If you see anything to do with sulfur being an impurity, which is making something not pure, in a fuel, for example, if you're trying to burn methane, but you realised your sample has got sulfur in it, well, that is going to react with the oxygen to make sulfur dioxide. So whenever you see sulfur, link to acid rain. And in fact, as well as sulfur dioxide, nitrogen oxides also cause acid rain. But these ones take place within a car engine. Okay, so very specifically, always put acid rain, but these take place within a car engine at very high temperatures. So we said before that 80% of the atmosphere is nitrogen. So if that goes in your car engine and reacts with oxygen, it can produce nitrogen oxides. It doesn't happen normally, like there's loads of nitrogen and oxygen in the air. They're not reacting normally, but they need really high temperatures. Both of these two can cause respiratory problems, so breathing problems as well. Carbon monoxide we came across earlier, CO, just one oxygen. That is toxic and it can kill people. Okay, it's called the silent killer because it's odorless, you can't smell it, and if your boiler at home is doing incomplete combustion because one of the pipes is blocked and it's not getting enough oxygen, you will be producing carbon monoxide, and that is toxic and can kill you. So we're going to look at using resources. So the first thing we're going to look at is a life cycle assessment. You can do this for any product that you are interested in. Again, something like a mobile phone, the company might be asked by the government or by the supplier to produce a life cycle assessment for that. So first of all, there's 4 factors. Raw materials. So these are things like, what are you using to make the phone? So it's all of the process involved in, for example, making the plastic. So for this one, you might be extracting crude oil, and you need to think about what effect that has on the environment. You might be using machinery to do that, which is burning fossil fuels and releasing carbon dioxide as you're doing that. You may well have to cut down trees to get to an area to mine it, for example, for the gold, for the connections that you're going to use within the electrical circuit of the phone. So there's loads of things that you can think about that will affect the environment when you're looking at the raw materials for the phone. The manufacturing and the packaging. So in all of these processes, they often involve some sort of factory which you need to power by burning fossil fuels to generate electricity. Again, that's going to be releasing carbon dioxide. It could also, if it's got sulfur impurities, be releasing sulfur dioxide, causing acid rain. And where's the packaging coming from? Where are you sourcing that from? That could link into deforestation again. Are you cutting down trees to generate your packaging? The use of the product. So can it be, is it just used once, for example, and then someone throws it away? Is it something that's used for a long time? When they're using it, are they needing to charge it up using electricity? Again, burning fossil fuels and all of these things. So this is thinking about when the product is being used by the consumer. And finally, at the end of the life cycle of the product, how are you going to get rid of it? Is it going to fill up landfill? Has it got toxic chemicals in it which need to be disposed of carefully? Or can you recycle it? So all of this process is showing the effect on the environment of that single product. Sustainable development. is linking into the resources and the resources that we're using, because it is the development that meets the needs of the present society without damaging future generations. You can imagine a tick box type thing in the foundation for this. So basically it means making sure that we're not digging up and mining the whole planet, chopping down all the trees and ruining it for future generations. We need to be sustainable. We need to make sure that we're using renewable resources where we can and not just exhausting all of our finite resources. Which brings us on to those two words. In chemistry, they use the word finite to describe non-renewable resources like fossil fuels. And in terms of making products and things, renewable resources would be our things such as wood and timber that we can replace. So if we're looking for sustainable development, we're going to want to reduce the finite resources that we're using and try and increase the renewable resources. And we want to try and do recycling as much as we can, because recycling means that less energy is used because we're not having to mine and dig for new materials. We're conserving the raw materials that we've got, which makes it more sustainable. And we're sending less waste to landfill. So recycling is really good for those three things. You need to know specifically about how glass is recycled. So you've probably been to the glass bins before, so you'll know the first point straight away, in that you separate the glass by the different colours of the bottles. So for glass recycling, the first step is to separate the glass by the colour. So you put green, brown and colourless glass in different bins. It's then crushed and melted, and then it's reshaped into new products. Okay, so that's a specific example you need to know about glass. Drinking water then, final couple of things in relation to water. Potable water is water that is safe to drink. Okay, so if you see the word potable, that means it's safe to drink. What that means it has low levels of salt, and microbes. So you might have a little bit of salt in there, a little bit of microbes or bacteria, but they are low enough levels that they are not going to cause any harm. It is not the same as pure water. Pure water would be just H2O, nothing else dissolved in it or anything tainting it. It's just H2O. So pure water, again linking back to the boiling points, would have a boiling point of 100 degrees. Potable water might not have a boiling point of 100 degrees because it might have a few other bits in it that increase the boiling point. Water sources. So surface water is one. In the UK, we have lots of surface water. We have lots of lakes, rivers and reservoirs to collect our fresh water, which is our rainwater in. We could also get water from groundwater, so underground rocks where water is stored. And to get it, to make sure it is potable, we have to go through a process of filtration. So a large wire mesh, which will get rid of large objects like twigs and, I don't know, trolleys, plastic bags, bottles, whatever else has been chucked in the river. Then we have to filter out the smaller solid bits. So we put that through a gravel and sand bed. So the water is filtered through there and other solid bits like smaller twigs and leaves and things will be removed. And then finally, we need to sterilize it to kill microbes. And there are several ways we could do that. We could use ultraviolet light that has enough energy to kill the bacteria. We could bubble it through with chlorine or bubble it through with ozone gas as well. So either of those methods or all of them we might use to sterilize the water. Then it is potable and safe to drink and we can put it through our taps. Now, in hotter countries, places like Saudi Arabia, for example, Dubai, where there's not a lot of rainfall, there are different steps you can take if there is not a lot of fresh water. And one of those steps is reverse osmosis. So normally osmosis would mean that the water would move from where there's a dilute solution, so a high concentration of water, to a low concentration of water. So normally, I'll just put normally there, that's the way the water would move. But with reverse osmosis, what they've done is they've taken salt water, which is over this side, which is from the sea, because they've got lots of sea water available. So they've taken their salty seawater and they've applied a great deal of pressure behind it, pushing it through a membrane, and that squeezes the water in the reverse direction of osmosis. Okay, in this direction. That's why they call it reverse osmosis. It goes against the gradient. Okay, so we require a lot of pressure for that. The other thing that they can do is distillation. Like we talked about before, they can take their salt water, heat it up, and make pure water. But in this case, it requires a lot of energy because you're burning fossil fuels to heat up the salty water. And it's therefore very expensive. So a lot of these hotter countries find it more difficult to get their drinking water, their potable water. Treating wastewater then. We produce a lot of waste, a lot of sewage water and things that we need to recycle because water is precious and we don't want to waste it. So we get a lot of waste from farmers and also from sewage systems, which we need to clear. So we first do a screening process, which is like a filtering process, really, to start off with, whereby we remove large objects from the wastewater. It then goes through a sedimentation process. And in this process, our wastewater separates into a sludge at the bottom, which is really thick. And then you get a fluffy layer on the top, which is called effluent. And you might have seen pictures about that, where this bit's really frothy and foamy and really light. So it just separates the products like so. Then there's two different processes. For the sludge, we do anaerobic digestion to break down all that waste material in the water. And for the effluent, we do aerobic digestion. So you might remember that the effluent is closer to the air because it's at the top. So that might be a good link to think that's the one that has aerobic digestion. So for the effluent, air is pumped into it. And then bacteria break down the effluent in aerobic conditions. For anaerobic digestion, and finally, the water is released back into the rivers. So the bacteria break down any waste product and then the water is released back into the rivers. For anaerobic digestion, if you are a separate scientist, you would have looked at this before in biogas generators. So this is where the link is between biogas generators for separate scientists. So bacteria break down the sludge, but this time in anaerobic conditions. And the two products are methane, which is a biogas, which can be used as a fuel, and fertilizer, which can be used by farmers to put nutrients back into the soil.